Welcome to this explainer on 17A, soil stabilization. Today, we're setting the stage for a really fascinating look at the invisible engineering that literally keeps our massive structures from sinking right into the mud. We're going to take a journey beneath the surface to explore exactly how humans have learned to master and, honestly, manipulate the very ground we walk on.
So, what exactly do you do when the earth beneath your feet is just too weak to hold up a building? It's a universal engineering dilemma, right? Every single structure we build, whether it's a tiny house or a massive superhighway, has to rest on soil. But here's the catch. Nature very rarely provides perfect conditions. Finding a site with naturally satisfactory soil right out of the gate, that is a super rare occurrence. Okay, let's dive into this. Here is our roadmap for today. We're going to cover the ground beneath us, fixing soil without additives, the power of cement, waterproofing with bitumen, chemical soil transformations, and finally, grouting and geosynthetics. Let's get to it. Section 1. The ground beneath us. So, what foundational choices do engineers actually face out in the field? When they hit unsatisfactory, weak soil, they basically have a menu of 4 options. Number 1, bypass the bad dirt entirely using deep piles. 2, scoop it all out and replace it with good soil. 3, redesign the entire structure to sort of float on top of that weak layer. Or 4, treat the soil. And today, our entire explainer is zooming in on that 4th option, the absolutely incredible science of treating and stabilizing the soil right where it sits. Moving on to Section 2, fixing soil without additives. Think of this as phase 1 of our engineering detective story. We're manipulating the existing soil using shear force and the elements. What's really fascinating here is how our stabilization toolkit splits right down the middle. Before we even touch the chemistry route of mixing in additives, engineers always try to fix the soil naturally first, either by mechanically rearranging it or by simply draining the water out. Mechanical stabilization is honestly a bit like baking. If your recipe lacks structure, sometimes you just need to stir it harder, or maybe balance out your dry and wet ingredients. Engineers can literally change the gradation of soil by blending coarse gravels, which give us that crucial friction and hardness, with fine binder soils, like clay, which act as the glue. Then they bring in the heavy machinery for dynamic compaction. They just violently squeeze out the air, packing all those particles into a super tight, dense state. But what if the ground is essentially soup? The strength of saturated soil absolutely plummets when that pore water pressure gets too high. To fix this, engineers use this mind-bending drainage technique called electroosmosis. Literally, they zap the ground. They pass a direct electric current straight through the saturated earth. This forces the trapped water to move toward a cathode where it can be pumped out. It's like magic. It instantly boosts the density and load-bearing strength of the dirt. And hey, if electricity doesn't do the trick, we can just harness the elements. By applying extreme thermal gradients, engineers can manipulate the earth on a massive macro-level scale. Get this, in some parts of the world, they actually burn liquid fuel in underground pipes to literally bake deep pockets of soil into these massive solid cylinders. Or, on the exact opposite end of the spectrum, wet clay can be frozen solid to create temporary ice piles and cofferdams. It literally stops sudden collapses while a building is being underpinned. Insane, right? Section 3, the power of cement. But sometimes sheer force and temperature just aren't enough, and that leads us right to the chemistry route. Adding Portland cement to soil is a lot like throwing flour into a wet dough recipe. It just binds everything together into a rigid mass. And you get different mixes depending on what you're trying to achieve. Soil cement is incredibly strong, used all over the world as a rigid base course for light traffic pavements. But add just a tiny pinch of cement and you get cement-modified soil, which basically just tames sticky, difficult clays. You can even press it into blocks for low-cost housing. It's super versatile. Next up, Section 4, waterproofing with bitumen. So moving on to our next additive, the crucial thing to understand here is that bitumen acts very differently depending on the soil you mix it with. It stabilizes in 2 totally distinct ways. If you've got loose, sandy soil that just falls apart, the bitumen steps in as a glue to bind those loose grains together. But if you're dealing with cohesive clay, the bitumen coats all those tiny particles, acting as a heavy-duty waterproofing agent to protect the clay's natural strength from water damage. Now, obviously you can't just pour thick, goopy asphalt straight into the dirt. It's usually way too viscous for that. It actually has to be heated up, emulsified, or cut back with a solvent, like gasoline, before you can blend it into the earth. Once you do, though, the result is this highly durable base layer. Whether you're making sand bitumen or soil bitumen, it is absolutely perfect for dry climates and light traffic roads. All right, Section 5, Chemical Soil Transformations.
Okay, but what if we want to change the very DNA of the dirt itself? This perfectly illustrates the strategic choices engineers have to make. Cement adds raw rigidity. Bitumen gives us waterproofing. But then we have lime. Lime is a chemical that fundamentally alters these sticky, highly difficult clays, chemically transforming them into something crumbly and way easier to work with out in the field.
And incredibly, you usually only need about 2 to 8% of hydrated lime to completely alter coarse-grained soils. Just 2 to 8%. And this isn't even a new idea. The Romans actually used the lime stabilization to build the Appian Way. Think about that for a second. A road that has literally survived as a major traffic artery for thousands of years entirely because of this one chemical transformation.
Beyond lime, we start getting into highly specialized chemicals. Salts, like calcium chloride, are hygroscopic. That basically means they suck moisture right out of the air to keep dirt roads from getting dusty. Plus, they actually lower the freezing point of water to stop those awful winter frost heaves. Then you have synthetic resins, which act purely as waterproofers. Think of them as a microscopic raincoat for the soil. They don't add any extra strength, but they guarantee the soil won't lose its natural dry strength the second a rainstorm hits.
Which brings us to our final stop, Section 6, Grouting and Geosynthetics. These are truly some of the most advanced, cutting-edge techniques in civil engineering. Just imagine the absolute magic of being able to fix a cracked, sinking foundation without ever picking up a single shovel. Well, that's injection stabilization, also known as grouting. Engineers pump liquid stabilizers, stuff like sodium silicate, cement, or bitumen, straight down into these invisible underground cracks and voids in the deep rock and soil. The liquid solidifies, and boom, it instantly boosts the foundation's strength and blocks underground water flow, all without excavating even a single scoop of dirt.
Now, let's tie this back to our mechanical understanding of soil. On its own, soil is pretty great at handling compression, right? It can take a lot of downward weight. But it has terrible tensile strength. It just pulls apart super easily. Enter geosynthetics. By wrapping raw sand or dirt in these specially fabricated synthetic fabrics, engineers give the soil massive tensile strength. They're basically taking loose, weak dirt and turning it into rock-solid construction elements used for huge coastal works, earth dams, and retaining walls. Which brings us to our final thought. Human ingenuity has literally found a way to tame the totally unpredictable earth beneath our feet. Whether we're zapping it with electricity, freezing it solid, altering its chemical DNA, or wrapping it up in synthetic armor. So, the next time you're cruising down a perfectly smooth highway, will you take a second to think about that hidden, highly engineered chemical and mechanical world right beneath your tires? Thanks for joining me on this explainer, and as always, keep your curiosity grounded.